button statuses. We'll look at the web application stack, then about styling and storing data in a database. Then we'll start working on the core application features, deal with dates, represent data visually inside charts, and then use widgets to interact with our application quickly. We'll look at time zone conversions, then do more charting using Plotly, and finally I'll show you how to publish your web application onto the internet so that you can use it from anywhere you might be. So let's begin with the first section. We are going to have a close look at the Raspberry Pi. First, we'll look at the specifications and the features of the Raspberry Pi. I'm also going to compare various Raspberry Pis together, that's various Raspberry Pi models together, and see what the differences and similarities are. I'm also going to compare the Raspberry Pi against the Arduino, because I expect that a lot of people doing this course are already familiar with the Arduino, and a question that I often get is, what are the differences? Which one should I be using, the Arduino or the Raspberry Pi, or both, and why? So we'll look at that in this lecture. We'll continue with the operating system. Unlike the Arduino, and here's one big difference, the Raspberry Pi needs an operating system to be useful. So this is what this section is for. We'll start with having a look at the various options that you can use, especially when it comes to the Raspberry Pi 3. There's a lot of different operating systems that you can use, so I'll have a look at some of the most common options. Then I'll explain the differences between the headless and a GUI, a graphical user interface type operating system, and I'll explain why in this course we have chosen to use the headless version of the Raspbian operating system. Of course, then I'll show you how to install the operating system on your Raspberry Pi's SD card and to connect to it from your host computer for the first time. Before we do any more work in this course, at this point I'm going to show you how to backup and recover the contents of your SD card. So backing up your SD card is a fairly straightforward process, although it does take a little bit of time, but it's like insurance. You will be investing a lot of time setting up your Raspberry Pi, the operating system, the various services and servers and software that make up your application, and of course you'll be writing a lot of code, and it'd be a shame to lose all that because perhaps an SD card becomes corrupted or there's some damage in the file system, and a lot of other things that often are out of your control. So I'm going to show you how to back up your SD card on the Mac OS and on Windows 10 just in case something bad happens. Of course, backing up your Raspberry Pi is only half of the whole process. You need to know how to restore your operating system, how to restore your SD card from a backup, and I'll be showing you how to do that also on Windows and on Mac OS. Time to start playing with the Raspberry Pi and its GPIOs now. So in this Python and GPIOs section, first we'll talk about what GPIOs are and the different types of numbering systems that are used, which is another difference between the Raspberry Pi and the Arduino. On the Raspberry Pi, there's a couple of different numbering systems and addressing systems for all the pins on the GPIO header. And in one of the lectures in this section, I'll explain how that works. And then we'll move into Python. Although the Raspberry Pi, because of its Linux operating system, has provision for pretty much any programming language that exists, the vast majority of documentation for the Raspberry Pi uses Python, and Python is the most common language used to work with the Raspberry Pi. As you'll see in this demonstration, in this lecture, using Python on the command line without even having to write a program is very easy and straightforward. So we're going to spend a bit of time on the command line, turning LEDs on and off and playing with buttons, and eventually working with libraries and the DHT22 sensor as an example of some more sophisticated sensor operation that you can perform again with Python. In the next section called the Web Application Stack, I'm going to introduce you to the Web Application Stack. So the Web Application Stack is the architecture on which we will be building our application. So I'll start first by explaining what the application stack is, then what the Python virtual environment is, which is another one of those mechanisms that the Raspberry Pi provides thanks to access to high-level development tools, unlike the Arduino, which makes it easy and safe for us to build multiple applications on the same piece of hardware, on the same computer. And later on in this section, I'll show you how to install, set up, and configure the basic components of our web application stack. And that's the Nginx web server, the Flask micro framework for building Python web applications, the UWSGI application server, and systemd for automatically starting our web application when the Raspberry Pi starts. Then we'll move on into the style and persisting section. In the style and persisting section, I'll show you how to use the skeleton boilerplate CSS system to make our application look good. Then I'll show you how to implement persistence using the SQLite 3 database engine. And finally, I'll show you how to deal with bugs, how to do debugging using the information that you can get from various log files or information that you see displayed on your browser. Now we are starting to actually work in building our application, and in the core application development section, we'll begin with the first page. We'll get data from our sensor and display it in the web browser so that we can easily check on the temperature and humidity of our lab. I'm also going to show you how to record this information in the database so that we can retrieve historical records. And of course, we don't want to have to manually grab information from our sensor and store them in the database. So I'm going to show you how to automate sensor measurements and creation of records in the database. As we are storing more and more environmental data records in the database, eventually we will develop the need to filter out those records according to dates and times. So in this section here, we'll do just that. I'll show you how to retrieve records from the database based on a specific date-time range. Then I'll show you how to use query strings to pass that date-time range information from your web browser to the server so that the server can react. And because we don't want to have to manually set the date-time ranges in the URL of our web browser, I'm going to show you how to use jQuery to create preset buttons that we can use so that we can easily navigate back in time. At this point, our application is becoming more sophisticated. We have already collected a lot of data from our sensors, and what I'd like to show you next is how to improve our application by first implementing Google Charts. So we'll use the Google Charts API to convert our raw data into nice looking line charts, and how to use the date time widget so we can easily define the date time range for the data that we are displaying in our browser. There's also provision for time zones. So by default, our application is time stamping our records using UTC, which is the convention when it comes to timekeeping on server machines. But of course, it will be useful to be able to convert those UTC times into our own local time zone to display that there is timestamps for records on the time zone of your computer. So I'm going to show you how to use jQuery plugins on the client side and Python modules on the server side in order for these two together to deal with time zones in our application. In this section on Plotly, I'm going to show you how to do data visualization and analysis using the Plotly Python library. So first, I'll explain what Plotly is and give you some examples of how you can use it on the command line. And then we'll start implementing a little bit more functionality in our application so that we can send sensor data to Plotly where it will be visualized. And while we're at it, I'm going to show you some more debugging tips and tricks that will help you a lot in dealing with inevitable bugs as you're working with applications of this kind. Now, last but definitely not least, at this point, we will have completed development of our application, and the Raspberry Pi 2 and much faster than the original Raspberry Pi. But once you go past this time-intensive compilation stage, the differences in speed are not as pronounced. So you can easily use an older Raspberry Pi. This one is an original Raspberry Pi version 1, Model B. It's about 3 or 4 years ago. Runs great. Everything just works fine. And this one is a Raspberry Pi 2, also Model B, and the same software works just nicely. So if you have a Raspberry Pi lying around, you can certainly use it for this project. It doesn't need to be the latest one. If you're curious, then it's good to know that I've also tested the application on this Raspberry Pi Zero W with the headers attached. The only limitation or the only difference here is that the Raspberry Pi W0 doesn't have a fixed wired Ethernet adapter, so you will have to rely on Wi-Fi Ethernet. But I do have information in the course on how to enable and set up Wi-Fi on your Raspberry Pi. So we can certainly go with a Raspberry Pi W0 as well. Apart from the Raspberry Pi itself, you will need an SD card. So a mini SD card or a micro SD card like this. This one is a 32 gigabytes, but I'm actually using an 8 gigabyte SD card here, since we'll be using a minimal version of the Raspbian operating system. The amount of space that it needs, the footprint that it has on the SD card is also minimal. So you can get away with an 8 gigabyte SD card. And it also doesn't need to be the latest. We're not doing anything that has intensive read and write operations on the SD card, apart from the original installation of the operating system and some downloads of source code. The rest is just the regular operations on the SD card. So you can also go for a cheaper SD card that you might have in your drawers. Other than the Raspberry Pi and the SD card, you will need a way to power your Raspberry Pi. So I'm using an adapter like this that I've spared from other devices. This is a Panasonic USB adapter that outputs 5 volt at 1.8 amps. Which is more than enough for the power requirements of this application. As you can see, the hardware that I've connected to the Raspberry Pi is minimal. It really takes no power at all, so you don't need a beefy power supply either. Of course, don't forget a mini USB cable to connect to your USB power adapter. Then you need a mini breadboard. You will need a DHT22 that we'll be using to get environmental data from. I decided to use a DHT22 sensor because it's so common. Most people seem to have one spare in the drawers anyway, and it's well supported on the Raspberry Pi with a very easy to use Python library. Of course, if you prefer, you can substitute the DHT22 with another sensor that you may have, as long as you can find an appropriate Python library. You'll be able to integrate it with the rest of the scripts that I'll be showing you in this course. But you can also do that at a later stage. So you can start with a DHT22 and follow along with the instructions in the course, and then as an extension, attach additional sensors. We also have a available here in this GitHub repository. If you're not familiar with what GitHub is, just think of it as a place where we can store and share files with everybody. It's a code repository website, and I've uploaded all the relevant files here so that you can simply either clone it. If you don't know what that means, then don't worry about it, or simply download those files as a zip file. When the download finishes, you'll have a directory that looks like this, which, as you can see, contains all of the contents that you see here on the GitHub repository and website. From here, you'll be able to look at individual files and copy them across over to your Raspberry Pi instead of having to type everything, and therefore severely reducing the risk of error. So here I've got things such as the Python scripts, I've got HTML files, I've got configuration files, let's see, like this cron scheduler, for example. I've got the text that you were putting into the cron scheduler. I've got information on how you can set up your Wi-Fi, either for Jessie, so that is Raspbian and Jessie, or Stretch, a lot of other things. There's also the template files, HTML, static files that you'll need like JavaScript and CSSs. It's all here. I even have a complete version of the application. So this is a complete copy of the application exactly as it's operating on my own Raspberry Pi. So you'll be able to restore from here really quickly if you need to. So as you're going through the course, it is a good idea to keep the GitHub repository for the course open in a window nearby, so you can just quickly go and pick up on the files that you need. There's also a wiring schematic here that will help you as you are assembling the small circuit that is part of this course. In some of the lectures where the commands that you'll be typing on the command line are longer, where the risk of error is higher, I've recorded those sessions here as text files so you can access them. So you can simply then just copy a command line and then paste it on your console, and simply just hit enter instead of copying manually the content from the screen. With all the files that you'll find in the repository, my objective was to ensure that you can spend a lot more time learning rather than trying to fix any typos or any syntax problems as you are typing in either the programs or the various commands of the command line or configurations. By setting up this repository, my objective was to ensure that I can maximize your learning time and minimize the frustration time that comes with mistyping a command or by introducing the wrong character at some part of a Python screen or something like that. Application on an original Raspberry Pi Model B, a Raspberry Pi Zero, Raspberry Pi 4 and a Raspberry Pi 3. On the software side though, there's a new operating system and newer versions of the various components that are distributed as apt packages or Python modules. There are also newer versions of the Python 3 interpreter, JavaScript libraries and cloud applications. The operating system is a major component of our application. When I published this course, the latest version of the Raspberry Pi operating system was Buster version 10.1. Today we have 64-bit versions of the Raspberry Pi OS Bullseye version 11. Upgrading from Raspberry Pi OS version 10 to version 11 is a major upgrade. Doing this kind of upgrade in place requires the replacement of millions of files and changes in configuration. Much of the process of an operating system upgrade is automated, but getting the application that is running well on an old operating system to continue to function well under the new operating system often requires a lot of work that is difficult to standardize and document so that you can follow and learn from. One of my objectives is to do a disciplined and minimal effort upgrade, so I opted to upgrade the operating system to the latest available version of Buster, which is currently version 10.13. If down the track I choose to use Bullseye for the full stack app, then I'll start with a fresh copy of the operating system on a new SD card and build up the application from there. This is something that I've actually done, but I only recommend it if you're starting from scratch. And I'll come back to this point later in this briefing. Luckily, the Raspberry Pi OS is built on Debian Linux, which uses the apt package manager. The full stack application depends on the Nginx web server and the SQLite 3 database server, and those are easily upgradable with apt. I'm also using apt to upgrade the Raspberry Pi OS to version 10.13. The full stack application is written in Python and uses the Python 3 interpreter. After extensive testing, I found that the newest version of Python that does not break any features in the application is Python 3.8.13. When I published this course, I used Python 3.8.1. Unfortunately, versions of Python that are 3.9 or newer break the Python wrapper for the RF24 transceiver module. As I wanted to keep all of the functionality of the application, I opted to upgrade to Python 3.8.13 and not the currently available latest version 3.10.5. I'll come back to this if I find a way to successfully compile the RF24 Python wrapper with Python 3.10 or newer. Once I had found the latest compatible version of Python 3, I upgraded all other Python modules and tested that they worked as expected. With the exception of the Adafruit DHT22 module, it is easy to update the Python modules. The Adafruit DHT22 module requires a hack if you are using a Raspberry Pi 4, and more about this later. I also upgraded the jQuery, Datetime Picker widget and the JS time zone detect JavaScript libraries that the application uses in the front end. Everything worked well here, and I was able to use the absolutely latest versions of these libraries. Finally, the full stack application interfaces with several cloud applications such as If This and That, Google Charts and Plotly. After updating the individual software components of the application, I restored and tested the cloud functionality. And I'm pleased to say that all cloud applications have made no breaking changes to the public APIs, so everything worked as expected. To help with the update process, I've created an update version tracker on Google Sheets. You can find this tracker by typing the short URL that you see on the screen here in your browser. Feel free to make a copy of the sheet so that you can edit it. I used this tracker as I was updating my own full stack application and captured the entire process in a new series of lecture videos. It contains before and after versions for the various components, information, URLs, and test and install commands for each one. I've recorded a series of new lectures to help you update your full stack application. You can find these lectures in a new section at the end of the course titled Full Stack Application Update. If you have already completed this course and you have a working full stack application, then you can consider updating it by following the instructions in the new update lectures. It's very likely that your starting point will be different to mine. For example, you may be starting from Raspberry Pi OS version 10.4 and Python 3.8.5, and that's okay. Be sure to start by taking a full backup of your SD card so that you can always start again if something goes wrong. I show you how to make and restore backups in the first part of the course. Once you have your backup, begin the update process as I'm showing in the new lectures. If you are starting this course now, you obviously don't have a full stack application to update. As you are starting from scratch, you'll be getting the latest versions of the various software components by default unless you specifically restrict the component version using the apt and PIP package managers. Please keep the information in this slide in mind as you go through the course. At the time I'm recording this briefing, I've not yet added reminders about these points in the original course lectures, so please try to remember. As far as the operating system is concerned, it is okay to use the latest available version. I've tested with the 32-bit version of Raspberry Pi 11, Bullseye, and the application worked well. It's also okay to use the latest available versions of Nginx and SQLite 3. The APIs for these components haven't changed. Be careful with the Python interpreter though. If you want to use the RF24 transceiver, then the latest Python interpreter that you can use is version 3.8.13. Watch the two new lectures at the end of the course titled Update System Python to 3.8.13, and the other one is titled Update Python Virtual Environment to version 3.8.13 for information on how to do this. For most other Python modules, it's okay to use the latest versions except for the following. The Adafruit DHT22 module is fixed to version 1.4.1. The Plotly module is fixed to version 3.10. The RF24 Python wrapper and module is fixed to version 1.4.3. And finally, the RF24 network Python wrapper and the module is fixed to version 1.0.17. For the JavaScript components, it's okay to go for the latest versions. In the update version tracker, you'll find command examples that show you how to restrict components to